All right, here we go. We are doing Quiz 7 review. All right, as always, in this unit, we need our beautiful z-score chart. So get this guy, bust it out, have it right next to you as we work through this lecture. Okay, so first up, in the diagram, the shaded region represents approximately 95% of the scores on a standardized test. Estimate the mean and the standard deviation. So right here, that is a massive clue. That 95% is saying these are the markers between plus or minus 2 standard deviations from the mean. So right here, this would be the +2 standard deviation marker, and this would be the -2 standard deviation marker. So just keeping that in mind. So if this is 2 standard deviations above and this is 2 below, they are 4 standard deviations apart. Okay, so first we want the mean. So the mean, we are adding these two values. We are averaging them. So we're adding them and dividing by 2. So 244 divided by 2 gets us 122. So our mean right smack in the middle is 122. Okay, to get to our standard deviation, again, we're given an observation value here that would have a z-score of -2 because it's 2 standard deviations below the mean. And then right here, this observation has a z-score of +2 because it's 2 standard deviations above the mean. So what I need to do to get to my standard deviation is take the difference between 170 and 74 and split it 4 ways, because between here and here, there are 4 standard deviations. I can even draw in those little notches, right? So here would be 1, here would be 2, here would be 3, here would be 4 standard deviations total. So we get to a difference of 96, split it 4 ways, and we get 24. So standard deviation would be 24. Okay, next, find the area under the normal curve within 1.6 z-scores of the mean. So if I sketch out a pretty picture, you know I love a nice diagram, so here we go. Here's my mean, the z-score is 0 right there. And we're saying within, so we're saying between these two markers. So here z is -1.6, and here it's +1.6, and we want the in between. So within would be anything that is less than 1.6 z-scores, standard deviations, from the mean. If I wrote this in my fancy notation, it would be like saying absolute value of z, or its magnitude, is less than 1.6. Or I could write it like this: z has to be between -1.6 and +1.6. So I'm trying to get to the area that's in between those two markers. So using my chart, if I look up a z-score of 1.6, it gives me this whole area to the left, and that gives me an area of 0.9452. If I look up a z-score of -1.6, that tells me the area below the -1.6, and that is 0.0548. I have to subtract out that hollow region because, again, here this is the area below the 1.6, and I have to cut out that hollow region, the area below the -1.6. So I get 0.8904. So 0.8904 would be the total area. All right, next up. So units in a large apartment complex vary in size. Let X equal the number of rooms in a randomly chosen large apartment complex. Use the probability distribution to answer each question below. So since I'm calling it a probability distribution, that means that we're representing all of our possible outcomes that could play out. We could have 1 room, we could have 2 rooms, we could have 3 rooms, we could have up to 7 rooms. So we're given the probability that goes with each room number. So here we need to know that together all of these probabilities, they have to add up to 1 since they represent all of the possibilities that could play out. So if I'm looking for this missing data point right in here, this missing probability, I need to do 1 minus all of these given stated probabilities all added up. So it ends up being 1 minus 0.81, and that leaves me with 0.19 right here. Okay, so I've filled in my missing probability. For 6 rooms, that's a probability of 0.19. So the probability of x equals 6, right? That's the 0.19 that I just solved for. Find the probability that x is greater than or equal to 3. So I'm going to add up all of these guys right here, or I can go through the complement and do 1 minus these 2 right in here. Either way, it's going to get me to the same end result. So if I add the 0.11 to the 0.14, the 0.25, the 0.19, and the 0.16, that gets me 0.85. So 0.85 would be that probability. Okay, write the event. Apartment has less than 4 rooms, so less than 4 rooms. In terms of x, what is the probability of this event? So less than 4 rooms would mean, well, x is less than 4. So I'd probably write it like that. So the probability that x is less than 4, now we have to solve for it. So less than 4 means it's 3 or below. So if I add up these 3 right here, I get 0.26. Okay, another way that I could write that, though, if it's less than 4, I could also say that it is 3 or less. So I could say that x is less than or equal to 3. I could write it like this, p of x less than or equal to 3, like that. That would equal 0.26. So this would just be another way of writing the exact same thing, right? It covers the outcomes of 1, 2, or 3. It does not include 4. All right, let me slide it up. Okay, a little practice with binomial and geometric distributions. So first up, we have a basketball player who makes 75% of his free throw shots during the season. If he shoots 6 free throws, and that's a huge detail right there. So if he shoots 6 free throw shots in tonight's game, find the probability that he makes exactly 4 free throw shots. So right here, that tells me right away that this is a binomial distribution because it's telling me a fixed number of trials, right? He's shooting 6 free throws total, and we're looking at, well, how many are successes? It could be 0, it could be 1, all the way up to all 6. So here we're asked to solve for, well, what if he makes exactly 4 of them? So what if x equals 4? Well, I can use my binom PDF function. So I can say, well, binom PDF, my n value, right, 6 free throws, probability of success is 0.75, and we're looking for exactly 4 of them. So when I type that into my calculator, 4 decimal spots, 0.2966. He makes at least 2 free throw shots, so at least 2. If I define that, flesh it out, that's telling me that he can make exactly 2, or 3, 4, 5, or all 6. So here, best to go through the complement, 1 minus the probability of 0 or 1. So 1 minus binom CDF 6.75, 1 or less. So that number right here is always 1 or less. So when I type that into my calculator, I get about 0.9954. Okay, next up, how many free throw shots do you expect him to make, and with what standard deviation? So we know that he's shooting 6 in the game, so what's the proportion of successes here? Okay, so we're just saying the mean would be n times p. So I'm looking at the number of trials multiplied by the number of successes. So 6 times 0.75. So the probability of success was 0.75. So trials times the probability of success gets us 4.5. So on average, right, we'd expect that he makes or she makes 4.5 free throws. And then we have to throw in our standard deviation as well. So standard deviation, big square root of NPQ. So standard deviation is the square root of 6 times 0.75 times 0.25. So n is our number of trials, p is the probability of success, q is that probability of failure. And when we type that in, we get about 1.0607. So again, if I wrote a sentence, I'm not going to do it here, but all I would be saying is, well, in the long run, on average, if this basketball player is shooting 6 free throws, we would expect him to make about 4.5 of them with a standard deviation of about 1.0607. All right, next example, a basketball player makes 64% of his free throws during the season. Find the probability that in tonight's game he makes his first free throw. So right there, that language tells me that this is geometric. So it's geometric because we have no fixed number of trials. We keep going until we achieve that specific result in the end. So if we're saying that first success happens on the second try, we're saying x equals 2. So now we can use our geometric, so geomet PDF, and here we can say that our probability of success is 0.64, and it happens on the second try. So if I go ahead and I crunch that, I should get about 0.2304. Okay, after his fourth attempt, so after the fourth attempt, so that means that that first success comes on the 5th try, the 6th try, the 7th try, the 8th try, etc. Right? Keeps going until he gets to that success, but he's not successful on the 1st, 2nd, 3rd, or 4th try. So here, easiest to go through the complement. So 1 minus the probability that he's successful 1st, 2nd, 3rd, or 4th try. So 1 minus geomet CDF, cumulative function this time. So 0.64 is that probability of success, and we're looking at on the 4th try or less. So if I type that in, so here I'll do it with you this time, I'll show you what I'm doing. So 1 minus second verse, I'm scrolling down to geomet CDF, cumulative right there, and I'm saying 0.64 is my probability of success, and success comes on the 4th try or less. So here we should get, we should get 0.0168. So pretty unlikely that this would play out. Okay, next up. Imagine he keeps shooting baskets until he makes a free throw shot. How long do you expect it will take, and with what standard deviation? So here, my mean, since it's geometric, is 1 over p, so 1 over 0.64. Okay, so that will get me 0.1, or 1 point, let me write that correctly, 1.5625. So 1.5625. 1.5625. So on average, in the long run, we would expect that it takes a little over 1.5 shots for him to make a free throw. And then with what standard deviation? So standard deviation is the square root of q over p squared. So I'm looking at big square root, 0.36 on top, right? It's the complement of the probability of success over 0.64 squared. So when I type that all in, I get 0.9375. So 0.9375. Okay. Please flip your sheet over or pull out that second page. Next. All right, here we go. So what percent of a standard normal model is found in each region? I could also say, what is the probability of this playing out? We see these types of problems phrased in a variety of different ways. Okay, it also helps to have a visual if you would like one. So if it's helpful for you, use a diagram. All right, what percent of a standard normal model is found in each region? So if I'm picturing this one, let me draw out my normal curve. Here's that mean where the z-score is 0. And we're looking at greater than a z-score of negative 2.4. So we're looking at this region right in here. So we know that we always have to do 1 minus the region that is to the left of it. So I'm doing 1 minus. And if I look up a z-score of negative 2.4, so right here, negative 2.4, this gives me the area, the proportion below. So I'm subtracting 0.0082. And that gets me 0.9918. And I write it as a percent, so 99.18%. Okay, here absolute value of z is greater than 1.1. So it's really telling you it's the magnitude. So it's saying that the distance from the mean, where the z-score is 0, is more than 1.1 z-scores or standard deviations away from the mean. So if I draw out my normal curve like this, mark the mean, z-score is 0, I'm just going to go 1.1 z-scores away in both directions. And again, let me say that back to you one more time. Whenever I see absolute value, it's telling me that it's a magnitude. The distance from the mean is more than 1.1 standard deviations away. So let me write that over here. Distance from the mean, where the z-score is 0, is more than 1.1 z-scores or standard deviations away. And again, whenever I see the beautiful bars like that, that signals to me, oh, we're looking at a magnitude, a distance from the mean. Okay, so I'm looking at more than this distance away, so I'm looking at the two tail regions, and I know that their areas are going to match. So if I look up a z-score of negative 1.1, that's going to give me an area of 0.1357, and it will be the same for this area over here. So 0.1357, so 0.2714 would be the total area in those regions. As a percent, 27.14%. Okay, next up. So here z is less than 1.2. So here is my normal curve. Here is my mean, where the z-score is 0, and here is my z-score of 1.2. And I'm saying less than. I love this one. It's the easiest variation because I get to go straight to my chart and look for it. So I get 0.8849, which will be 88.49%. Okay, next, absolute value of z is less than negative 1.9. Whenever I see the absolute value bars, right, it tells me, oh, this is a magnitude. right? A distance from the mean. So we're saying, okay, the magnitude has to be less than negative 1.9. And we know, oh, that seems just funny, right? That's not going to work. A number that is positive, because those bars force it positive, can't be less than something negative. So this is impossible. Let me just write that out in words. Let me draw my beautiful curve as well. So here we're saying a number that is forced to be positive cannot be less than a negative number. That would be impossible. So I would have nothing shaded underneath my curve, and that would give me a beautiful 0% right there. Okay, next up, we're looking at sweet little baby kitties. Sweet baby kitties. Okay, a healthy 10-week-old domestic kitten weighs an average of 24.5 ounces with a standard deviation of 5 ounces. Assume healthy 10-week-old kitten weight is approximately normally distributed. So again, I'm just going to summarize that off to the side. Normal distribution, 24.5, 5, like that. Okay, so here we're saying what weight corresponds to the 6th decile. What weight? So we're solving for x, we're solving for the observation, and we're told 6th decile. So the 6th decile is really the 60th percentile, which means that we're looking at where is the area below equal to 0.6, and what is the z-score that goes with it? We know that ultimately we're using x equals the mean plus the z-score times the standard deviation structure. So if I look for an area of 0.6, area of 0.6 puts me right about in here. And which one is it closer to? It's closer to the 0.3. So we're going to go with a z-score of 0.3. Z is about 0.3. So I know my mean, I know my standard deviation. I needed my z-score to find the x value, the observation, which is weight in this context. So x equals the mean, so 24.5, plus the z-score of 0.3 times the standard deviation, which was 5. So when I plug all that into my calculator and I hit enter, I get 26. Got a nice clean integer value here. So 26 ounces. So 60% of sweet, healthy, 10-week-old baby kitties have a weight of 26 ounces or less. Okay, for B, what percent of healthy 10-week-old kittens weigh between 21 and 32 ounces? So here we're in the in-between space. So I need to find both of those z-scores. So the first one, z equals the observation, 21, minus the mean, 24.5, divided by the standard deviation of 5. And I get a negative 0.7. For the other one, z equals the observation, so 32, minus the mean, 24.5, over the standard deviation of 5. Gets me 1.5. So I have the two z-scores, and now I need to go to my chart. So if I look up the larger one, the 1.5, I can see that the proportion below it is 0.9332. So I'm going to start with that, 0.9332. So that is the area below a z-score of 1.5. Now I need the area below a z-score of negative 0.7. So if I look at negative 0.7 on my chart, the proportion below is 0.242. So when I crunch that, I get 0.6912, or 69.12%. All right, next up. Okay, a kitten whose weight is in the top 10% of the distributions of weights is considered to be overweight. Poor baby kitty. what is the cutoff point for the weight of an overweight kitten? So top 10%, we always have to convert that to what it looks like below it. So top 10% would be the same marker as the bottom 90%. To better visualize that, you could always take a nice, beautiful, normal curve like that. Put a marker here. Right, that would have been the top 10%, which means that here's that lower 90% right in there. So I'm looking at the area below at 0.9, and I'm going to need the z-score that goes with it. So if I try to look up the 0.9 on my z-score chart, area of 0.9, let me pull it so you can actually see it. So right here, I can see that the z-score would be about a 1.3. All right, so then I'm looking for what is the cutoff point for the weight of an overweight kitten. So I'm solving for x, I'm solving for the observation. So x equals the mean plus the z-score times the standard deviation. So x equals the mean, which is 24.5, plus the z-score of 1.3 times the standard deviation of 5. And that gets me 31. So I get 31 ounces. So a sweet baby kitty who is 10 weeks old, who has a weight of 31 ounces or less, right? That would be the 90th percentile. So we're saying that 90% of kitties have a weight of 31 ounces or less. So any kitty that's above that marker, that threshold, is likely to be put on a little kitty diet. All right, next up. If 500 healthy 10-week-old kittens are selected at random, how many will weigh more than 22 ounces? So first I have to find the proportion of these sweet baby kitties that weigh more than 22 ounces. So I need to figure out, again, what's the z-score? So z equals 22 minus 24.5 over 5. So I get a negative 0.5 for my z-score. Okay, I'm looking at weigh more than 22 ounces. So if I look up a z-score of negative 0.5, it's going to tell me the proportion that weigh less. So I have to do 1 minus looking up the z-score of negative 0.5. So that gives me a 0.3085 as the proportion that falls below it. So I'm going to end up with 0.6915 as the proportion of 10-week-old healthy baby kitties who weigh more than 22 ounces. And since I'm asked for, well, say we had 500 of them at random, how many would we expect to have a weight that's more than 22 ounces? I'm just going to take that 0.6915, multiply it by 500, and get 345.75. So I can't have a portion of a kitty, so I round to my nearest integer value. So I'm going to say, well, that's about 346 kittens. All right, last up for our review today. What is the IQR of healthy 10-week-old kittens? So remember that IQR is the difference between the quartiles, the Q3 minus the Q1, which is really the 75th percentile minus the 25th percentile. So I need to figure out area below a marker of 0.75 and area below a marker of 0.25. So we've done this several times, so we should know what the z-scores are, right? We know that they're going to be opposites. This one's going to be the 0.7, and this one will be the negative 0.7 approximately. So now I need to solve for those two markers. So x equals 24.5 plus 0.7 times 5 gets me 28 ounces. So 28 ounces would be the third quartile or the 75th percentile. Okay, over here, x equals 24.5 plus a negative 0.7 times 5. So that's giving me 21 ounces right here as my marker for the 25th percentile or the first quartile. So to find the IQR, I'm taking 28 and I'm subtracting 21, and that gets me 7. So 7 ounces would represent the range for the middle half of data, the middle 50% of sweet baby kitties and their weights. All right, that's all I got for you today. I hope you feel reviewed, refreshed, and I hope you have a wonderful rest of your day.